I may this Thursday spend one of the 2 hours with you and just say, let's go sit at the computers, you guys work, and we try to debug any more problems, whether they be fundamental solving the differential equation kinds of problems, or if you're beyond that, then getting it so you get an aesthetically pleasing output, trying to think about how to do that. And, the ultimate goal, for some potentials, this may not work so well, but the ultimate goal is to get something that is kind of like Griffith's figure for the harmonic oscillator, where you've got the psi 0, psi 1, psi 2, psi 3 showing where the energies appear and the potential shape shown all in the same figure. For some potentials, of course, if your energy eigenvalues end up too close to each other and they're not all nicely spread apart, then it's kind of a mess to draw all the wave functions, because you either have to make the amplitudes really small or have them go on top of each other. But we can think about that if that's the case for yours. But first, of course, you want to try to mimic what's going on with the harmonic oscillator, because if you can get that working and everything looks right, your code is in all likelihood working perfectly. And then you can switch your potential to something else at the last minute. And you're always welcome to change your mind on the potential if it, for some reason isn't suitable or doesn't give an aesthetically pleasing output. Okay. So we're heading into chapter 3. And again, I'm sort of, the last 3 times I've taught this course, I talked about the Dirac orthonormalized vectors, or, energy eigenfunctions, before we got into chapter 3. And every time I've been a little bit disappointed about how I felt like it went over with the class. So I keep thinking about how I can reshape it in the future, and maybe I'm still doing too much with it. But the idea is, at the beginning of chapter 3, we're going to talk a little bit about mathematics, and it's going to be related to ideas that you may be familiar with from linear algebra, if you've taken linear algebra, but certainly ideas you just come across in physics, that of vectors and matrix operators or linear operators on that vector space. So let's just kind of talk in general about that stuff. And I'll probably just work at the board and do some examples at the board for a little bit. I guess the first thing I want to do is go back to, I think we did this voting question before, but just to remind you of it, here's some wave form, like the wave function shape at time t equals 0. And as we've done, 100 times, we're trying to write it as a linear combination of time-independent Schrodinger equation solutions in the manner shown at the top. And how do we compare the information contained in psi of x0 compared to the information contained in the coefficients, if we know all the coefficients, versus knowing psi of x0? Just give me a quick show of hands, because I think we did do this one before. Yeah, you can vote with numbers for A, B, C, D, 1, 2, 3, 4 if you want. That'll make it clear. Okay, so there's some disagreement in the class. It looks like it's between B and C, I think, are the most popular ones, but I think C had the majority there. And the answer is they have the same information. Clearly, if I know these functions, right, we're assuming we know what these definite energy states are. If somebody gives me the CNs, then this is a formula for how to construct psi of x0. So the CNs have as much information as psi of x0, but we also derived a formula for CNs that told us if somebody gives us psi of x0, you can calculate the CNs one at a time. And so psi of x0 and CN actually contain the information, the same information. you can reconstruct the other if someone gives you one. And so in some sense, they're equivalent descriptions of the same thing. And we're going to kind of elaborate on that now in a manner that you've probably thought about before. You know, if I've got a vector, let's go back to our old-fashioned notation. We're going to change our notation for vectors in quantum mechanics. If I want to, one way to represent that vector, rather than just drawing an arrow, is to give x, y components. And of course, to do that, I'm going to choose x, y axes. That's going to determine the components. So I could say, in this set of axes, here's what I'm choosing my x, y axes to be. This vector will have, you know, certain components, x and y components. But I don't have to choose those axes, right? I might have chosen, you know, some tilted axes, something that looks like this. And I might call this x prime and y prime. And it would be a perfectly good description of that vector to give either the xy components or the x prime y prime components. They both have the same information. They're describing the same state. And the point is, for what we're doing now is not just changing basis, but we have here a notation for a vector that's saying we're talking about the same thing. And I want to be able to write down the thing we're talking about, even though I might represent it a bunch of different ways. Even though in quantum mechanics, I might represent it by giving you the CNs or psi of x0, or maybe some other function that we'll see in just a second, okay? So we're going to, in quantum mechanics, start developing what's called Dirac notation. And that is, we'll put a symbol in between a vertical line and a sort of angle bracket there. And that's just going to be our equivalent notation. We'll find out it's more convenient than doing things like this. Sort of a lot of operations sort of tell you how to do the operation by itself. Okay, so just like I could give the components of this vector v in various different bases, right? The x hat, y hat basis, or the x prime, y prime hat basis. Just, it's the same way that I could, you know, write this vector as a linear combination of x hat and y hat. And those coefficients that go in front of that expansion is what we call the components of that vector. And so we're going to think of it the same way, components in a particular basis. So here's one description of a state at a particular time. If I write it as, thinking of the infinite square well here, Cn psi n of x, then this is another description of the same state. Give me a collection of Cn's for all n's, right? That's a different way of specifying the same state. I might have, instead of wanting to expand it this way, I might have wanted to write that state as a linear combination, phi of k, times e to the I kx. And as you know, we conventionally put a 1 over root 2 pi out in front. These are like coefficients in front of these functions. And we're going to sum over all coefficients there. We have a continuum of functions. And here again, we're thinking of this, well, we normally want to include the 1 over root 2 pi based on our discussion for Dirac orthonormality. We're going to keep those two things together. But these are the expansion coefficients. So I could give this, that's one representation. I could give this, that's another representation. I could give phi of k as a function. I guess I don't need to write it in set notation, but you know, phi of k as a function of all k. Just give me that function of k. And we'll give 3 different representations. So we want to have a notation that allows us to specify what the thing is we're trying to describe, no matter what the representation is that we use. Okay, so let's try to develop some notation for basis vectors. As you know, in introductory physics, the basis vectors, we also give them kind of an abstract notation, right? I might say in introductory physics, here's how I denote a vector. We write the basis vectors like this, either x hat, y hat, z hat, or I hat, j hat, k hat sometimes. Here we're going to be writing vectors like this in this course. And using x's, y's, and z's isn't so good because we're going to be having infinite collections of basis vectors. So I want something kind of with an index on it that I can sum over. I don't want something where the letter changes every time. So we're going to sort of, if we were in a three-dimensional vector space, I might denote the basis vectors like this. E1, E2, and E3. Okay, and if I wanted to say I can write this as a linear combination of this basis vectors, I might say something like this. I can write V as its x component times x hat plus its y component times y hat plus its z component times z hat, right? That's something you do in introductory physics. How would we write the same kind of thing in this new notation? Well, we would say V is equal to let's just write it out. V1 times E1 plus V2 times E2 plus V3, these are the components of that vector in this basis, E1, E2, E3. And that's kind of nice because I can write this in summation notation. We're not going to want to write things out explicitly like that once we get infinite series, right? It's okay for 3 dimensions, but I can write this as the sum from 1 to infinity, sum from 1 to 3 of VI, I guess it's n here, En, Vn, En. So this is just saying I've got a vector, and I'm expanding it as a linear combination of the basis vectors, and these are what we call the components, right? We're just going to write sums like that because normally we're going to be doing an infinite sum. We don't want to write things out term by term by term. Okay. This is like, of course, writing some state. And again, whatever symbol you put in here, in quantum mechanics, you can choose that symbol, just like you can, if you have a vector that you want to talk about, you could say, that's the vector A, or I might put a P on it if I want it to remind me of momentum. But it's always for me, right? The notation for an abstract vector is something that reminds you of it. So if I want to write an abstract description of something like psi of x0, maybe I'll choose to put the letter psi in there just to remind me of what it means, right? I'm representing, this is only one way I might represent this state. And this state is going to be the same state no matter which representation I use, whether I'm giving you the CNs or whatever, we're talking about one kind of state. So we've seen this before. If we're talking about the harmonic oscillator, maybe I start at 0, Cn, psi n of x, and these psi n's I'm talking about for the simple harmonic oscillator, the ones appropriate for that. We've also seen that for the free particle, I might write a state as an infinite linear combination of, Dirac orthonormalized usually, states of definite k. So this is a state of definite wave number. I'm going to take an infinite linear combination of these for different k's, and these are the coefficients. Okay, so we're generalizing this kind of idea, which is a generalization of just the simple old writing things as a linear combination of basis elements. But we're in this class, the difference is, usually in introductory physics, once you choose an x, y, and z hat directions, you don't switch them. And in quantum mechanics, we're always going to be changing our mind about what basis we want to use. We'll have one basis for that's convenient for position measurements, one for momentum measurements, one for total energy measurements. Those are the big three that we'll use. So we've got to get used to switching bases. Okay, so we're going to talk a little bit more about the ideas in linear algebra, and we're going to generalize them to infinite dimensional bases, which makes things a little bit more complicated than if you've taken that linear algebra class here. You're always talking about finite dimensional vector spaces. In infinite dimensions, things are a little bit more, well, that's an understatement, a lot more complicated. And we're going to try to not get into too many details of it. But let's talk about vector spaces, right? Here is a vector. It's an element of some vector space. In order to know how many basis vectors I need to know what the collection of all vectors are, right? So if we're in 3-dimension and we want to be able to point from the origin to any point in space, we need a 3-dimensional vector space. So if you Google axioms for a vector space, they're going to tell you, we usually in physics, we don't think about the axioms too much, but you'll find that you assume all of these almost without even thinking. Most of them are so obvious. If I multiply, so in this slide, I've made all my vectors boldface, and I know it's a little bit hard to tell, but non-bolded things are supposed to be scalars. So if I, for example, scalar multiply a vector, which I'm calling x here, by the scalar 0, it turns into what we call the 0 vector. Yeah, I mean, it's a vector of 0 length. If you scalar multiply it by 0, I get a vector of 0 length, and we call that the 0 vector. Up here, we're being told that we're going to assume that there is something called the 0 vector. And what defines it is it's the vector that if you add it to anything, you get that thing back again. It doesn't do anything when you add it onto something, right? There are some how to distribute scalars over sums of vectors and how to distribute sums of scalars over a single vector, and all those things you do without thinking too much. Now, the one that we're going to want to really concentrate on here is closure. And usually this isn't too much of a problem in finite dimensions, but we might find that we want to describe a collection of vectors, and they aren't closed under addition and scalar multiplications. Now, you've always got to specify what the scalars are. Usually when we're talking in 3 dimensions in intro physics, our scalars are real numbers, right? But, for example, if I said, I'm going to think of a vector space, and the collection of all vectors in this room, let's say the origin is down here on the floor, is the collection of all vectors that point from the origin somewhat upward in the room. Okay, seems like a perfectly good collection of vectors. Unfortunately, it's not closed under addition and scalar multiplication. It certainly is closed under addition. If I take the sum of any 2 vectors that point up, I'll get another vector that points generally up, right? But what about scalar multiplication? Well, if we're talking about scalar multiplication under the real numbers, certainly one real number is -1. If I scalar multiply by -1, it switches the direction, and then it would point down. It wouldn't be in my collection. So my collection, even though I can verbally describe it like that, it's not closed under addition and scalar multiplication. And a lot of times that causes problems. So the worksheet that I passed out, who didn't get this worksheet called vector spaces? I think, yeah. Oh, and you didn't get a copy of the notes either. Let's just do problem 1. I want you to think about it. You can talk to your neighbors about it here. Here, what I'm doing is describing in words a collection of things. Now, they don't have to be vectors like arrows in 3 dimensions. They could just be a collection of objects. And the claim is, when I describe it, you'll know what I mean by addition, right? If you add 2 functions, you get a new function, right? Which is the sum of those 2 functions. If you scalar multiply a function by 3, you get a function that's 3 times as tall, right? It goes up 3 times as high. So we know how to add and scalar multiply functions. the question is, in A through E, is the verbal description I'm giving there a vector space? And in a couple of cases, I've switched my mind about the whether or not we want the scalars to be involved. In other words, when you scalar multiply, are you allowed to multiply by complex numbers or real numbers? And in the first question, A, I'm asking the same question for the same set of functions, but saying when we say a vector space over the real numbers, that means these scalars that you put out in front of the basis vectors have to be real numbers. If I say a vector space over the complex numbers, that means you're allowed to scalar multiply by complex numbers. So think about those. I mean, it's a little bit of a strange abstract concept, but the things we're talking about here, we want to call vectors, but whether or not the collection that's described is a vector space depends on, most crucially, that closure axiom. So think about whether it's closed under addition and scalar multiplication for the collection of scalars that's specified. And just answer yes or no. And I was going to get Yi Chen a copy of these. Now, Yi Chen, I can't remember. We probably talked about this before, but they're posted on the website. If you like looking at those on your tablet, feel free to just go to the website and annotate on your tablet. Just to make sure we're on the right page, what do you guys say about 1a over the complex numbers? We're saying my potential vectors, every vector in a space is a function with only real outputs at every x, right? So we're taking the usual x-axis that has real numbers on it, but the output can only be real. If I say I'm going to allow linear combinations with complex coefficients, if I take two vectors in that collection that I've described, real function, some functions with real outputs, will any linear combination be a function with real outputs? Not if I allow, you know, I would say something like this. It's supposed to be closed under scalar multiplication. If I take the function sine of x, hey, that should be a vector in my vector space, right? Or at least my potential vector space. But if we're saying is it a vector space over the complex numbers, there's scalar multiplication, I times sine of x by a complex number. And that's not, this thing is not in my verbal description of all the vectors. So what I've described is not a vector space because it's not closed. Usually that's the problem we'll have when we make a verbal description. It is closed over the real numbers though. So it is a vector space there. You don't have to check all those axioms. You'll find, oh, I know exactly how to do this. And it does work out, right? Usually all these other axioms you'll just do without thinking, even on functions. Normalized functions means the integral of f star of x times f of x from minus infinity to infinity equals 1, right? Yichen, you understand what's being asked there? It is not. Is that what she said? Yeah, I wouldn't call it a vector space because some of these are going to end up being vector spaces and some not. But you could say it's a collection of things. In this case, mostly functions, right? And we want to say, is that collection that I've described in words a vector space?
So you want to ask whether that's a vector space?
Yes, whether the collection of those functions is a vector space. And really, you want to concentrate on closure. The other things, of course, they're for all these things, the zero vector is going to be the zero function. And you know how to add functions together. You know, when you multiply a constant times the sum of two functions, you can always distribute it over. So all those things will sort of come through. But the real question is whether the collection is closed under taking sums and scalar multiples for the scalar that's described. In quantum, we will always be talking about complex scalars.
So we are talking about like if we give a function a complex
We're not giving it a complex input because we're still thinking of them as functions of real x's. Okay. And whether the output can be complex depends on the problem, right? But if I take a real function and I scalar multiply it by a complex number like I, then it turns into a function that doesn't have real outputs anymore, right? It has purely imaginary outputs if it started out with real outputs. Mm-hmm. Okay, I know you're not all done, but I feel like I want to discuss together, and you can bring up the questions that you're exactly struggling with to try to illustrate this. So the question A here, set of all functions with real outputs at every x. And we're, again, always when we're talking about functions of x, we mean the x itself is real, but the output might potentially be a complex number like e to the I kx, or it might be a real number like sine of x. And we have to really think about the difference between those two. So the set of all functions with real outputs at every x, like sine of x, is not closed over the complex numbers because I could multiply by I, and then it wouldn't be one of those things in my verbal description, one of the things that I described the collection of. But it is, it would be closed over the real numbers. In other words, if I take any function with just real outputs and I scalar multiply by any real number, it stays one of those things. And if I add any two real output functions together, I get another real output function. So it's closed under addition and scalar multiplication. B, the set of all normalized functions. So that means the set of all functions where this, the area under the magnitude squared of the curve is equal to 1. What do you say about that? Is that a vector space over the complex numbers, that collection that I'm describing? Functions that satisfy that? Said yes. So that would mean that if I, for example, took 3 times f of x, maybe we'll call that g of x, right? That better also be a function that's in this collection. Now, is it satisfy every function in my collection has to satisfy this? So is that satisfied for this new function, which is just a scalar multiple of the old one? No, it's not going to be. This is going to be 9 times as big, so the output would be 9 there. So if you take, if you double a number in it, this says over the complex numbers, but 2 is certainly a complex number. It happens to be in the real subset of the complex numbers. It's not going to be normalized anymore. Only if I take a complex number of magnitude 1 and scalar multiply it, but any one that's not of magnitude 1. So the answer to B is no. It's not a vector space over the complex numbers. Because if it's normalized, if I multiply it by some non-unit size number, it's going to not be normalized anymore. And then it won't be in the collection that's described. What about C? I'm thinking of all the functions. And here we're talking about, I guess we could limit it to real output functions just so that we could visualize them. But here's 5. We're talking about all the real functions that asymptotically approach 5 as x goes to plus or minus infinity. I guess it's got to go that way on this side too. Is that collection going to be closed under addition and scalar multiplication? No, it won't, because if I add 2 of those functions, won't I get one that asymptotically approaches 10? And so it's not in the collection I described. And therefore, the collection that I described with a sentence is not closed under addition in this case, for example. What about the collection of all functions that go to 0 asymptotically as x goes to plus or minus infinity? They will be closed under both addition and scalar multiplication, right? If I have a function that instead of asymptotically going to 5, asymptotically goes to 0. If I add it to another function that asymptotically goes to 0, the sum will asymptotically go to 0. And if I multiply this function by 100, it's still going to asymptotically go to 0 as you go off to plus or minus infinity. So it seems like it's closed. And therefore, it sounds like it's a vector space, even for the complex numbers, right? It doesn't matter if this function, it starts getting multiplied in the I direction, but it's still going to 0 in magnitude as you go out there if the original function went to 0. E, the set of all continuous functions. If I add 2 continuous functions, do I get a continuous function? Yeah, right? If the left and right limits match the value of the function in the middle, that's what it means to be continuous. If I take 2 of those functions, then the left and right limits separately will go to, the sum. You add the 2 functions together, and scalar multiplication, scalar multiples of continuous functions are continuous. Okay, we're not going to be wrestling with these kinds of problems, but these are the kinds of issues we're going to have to really think a little bit more carefully about now that we're talking about much bigger vector spaces where we're not just thinking of something that has only 3 components, but rather we're going to take functions themselves to be our vectors. So we've got to get used to thinking that way, or at least that's one way to represent our vectors. Okay, back to the notes. Okay, so we've written that. On the 3rd page of the notes, there's kind of a summary sheet talking about a lot of different concepts associated with vector spaces, some of which you're familiar with and some most likely not, and the examples that we're going to use in quantum mechanics. So if you like, you can follow along with that and let me know if I missed something as I'm going through. Oh, I see. I wanted to say one more thing at the bottom of this page. So usually when we're specifying a vector, just as we do when we're behaving, describing things in 3-dimensional space, when you want to say, what vector am I talking about? The most convenient way to do it is in a particular basis. Even though there's no reason to be super attached to any one basis for describing a momentum vector, right? Or a position vector. I don't need to be slavish to the x-axis is that way and the y-axis is that way and z is up. I could always switch my mind and use a rotated frame if that's more convenient. Still, if I want to tell someone what vector I'm thinking of, giving them the abstract notation doesn't give them any information, right? It just says, oh, you're thinking of some vector. That's all I know about it. If you want to tell them what vector you're thinking of, you have to use some basis. And so most of the time, we will specify vectors in a particular kind of basis. And here are three ways that arise in quantum mechanics. The first way is the way we started out thinking of a particular vector, which is going to represent a state of a particle, giving a function of x. And in quantum mechanics, we know in order for it to represent a state for a single particle, this has got to be what we call square integrable. That means, I'm talking about the collection of all functions of x such that the integral from -infinity to infinity of f star of x, these could be complex numbers, times f of x dx is perfectly finite. That means it's normalizable. Another way to say that is they're not normalized functions, but at least we could normalize them, right? In mathematics, though, that collection of functions, which we're thinking of as kind of like our psi of x0, is denoted by capital L2, and usually you give, the domain of the function in parentheses. I don't think you'll see this notation in Griffiths, but you will see it in other quantum mechanics textbooks sometimes. So capital L2 means the 2 up there means the square integral part. So functions that are square integrable on the interval from -infinity to infinity. That's one way we're going to represent a state, right, or a vector for us. Another way we're going to represent it is by saying, oh, well, we've already mentioned that if you've got some energy eigenstates, you can always write your state as a linear combination, thinking of the harmonic oscillator, of those energy eigenstates, and the CNs themselves are a perfectly valid representation of the state. It's another way of representing the same state, right? I could have given it as a function of x, but I could also give you the CNs. Okay, so let's think of this is a sequence of numbers. They're complex numbers, right? They're a sequence of numbers. Now, they can't be any old numbers. In other words, I can't have all of these CNs be 1, or this series isn't going to converge. In fact, we already showed that it certainly is true that these CNs magnitude squared represent probabilities, and if I sum over all n's, I get 1, because that's what probabilities do. They've got to all add to 1. So there's another way to represent the function, a state, and that is by giving the CNs. And when we represent vectors that particular way, we are thinking of a different kind of way to represent the state that's called little L2. This is like a script L. And that is the set of all complex sequences such that the sum over all of them, you have to use the correct lowest index there, of the magnitude of Cn squared is finite. It's not necessarily equal to 1, because if this function weren't normalized, then these aren't going to be properly normalized, and it might add to 4 or something like that when you add up all the magnitude Cn squares. But at least this is a potentially normalizable function. Okay, so little L2 is giving a sequence of complex numbers, and that's one way to represent a state. Capital L2 is giving a function of x, and that's another perfectly good way to represent a state. Okay, and those are the two big ways we've done so far, because I could also think of, just like this is giving a function of x, this is a different way and a different basis of giving a function of some parameter. Now, we're not going to use them right now, but we're also going to be interested in finite dimensional vector spaces later on when we talk about spin. As you know, if you have a spin 1/2 particle, there are two linearly independent definite states of definite z spin angular momentum. And so we're also going to define things like C3. So this is complex numbers, three-dimensional complex vector space. That's just like our three-dimensional real vector space, except the scalars can be complex numbers there. So this is the collection of all triplets of complex numbers. Somebody in the, I guess I should mention, only one person did reading responses for today, and I did look before
Actually,
class.
I myself did. I was just late to the punch.
Oh, okay. Yeah, I looked this morning, and the one question I saw was about the term tuples. I guess Griffiths used the term tuple. So, when you give a collection of numbers separated by commas, right? If I say 3, 4.2, 7, in parentheses like that, I would say that's a triple or triplet of numbers, right? So if you wanted to generalize to, I could have n numbers, you might call that an n tuple of numbers, like a quadruple. N tuple means there's n of them just separated by commas. So this would be something like giving 3 complex numbers here. And I don't know how to denote this, but these aren't the same C's I'm talking about up there, but just complex numbers such that Ci is complex. Okay, so that would be a three-dimensional complex vector space. So we'll talk about C2 when we're talking about spin 1/2 particles. We'll talk about C5 too, a 5-dimensional complex vector space. So we're going to run through these examples, and you'll see on that third page, I am giving examples associated with those 3 cases because the finite dimensional case seems a little bit different. Okay. I have some things mixed between worksheets here. And what I want to do is just get used to thinking of examples in these 3 cases, capital L2, little l2, and the finite dimensional C's. Here I'm talking about C3. So what I want you to do is problems 1, 2, and 3 on here, which is just saying, hey, give me some examples. Show me how you add vectors in those spaces. Show me how you scalar multiply here by the number 2i. And I guess I should have said here, these are allowed to have complex outputs. We're still imagining the x is real, but the output of this could be complex. So in one, you're supposed to give 2 elements of little l2. That means you're going to give 2 sequences, and you're going to have to put some ellipses in there, ... You get the idea after a while. And they've all, if I call this square integrable functions, we might call this square summable functions, right? So this is the collection of all square summable complex sequences. So write down a complex sequence that that if you took the magnitude squared of it and added it up, it would definitely be something finite. And then another one, and then add your 2 examples. And then scalar multiply the second example by the number 2i. I mean, when you're writing a sequence, you could just as well write it as an infinity tuple, right? It's sort of like the stuff never ends in this sequence, right? So at some point you need a dot, dot, dot in there. Okay, just for number one, to make sure we're all on the same page, somebody help me write down an element. So I'm thinking of problem 1A, or before I even add them. No, I guess A, I'm supposed to specify them. So for 1A, what's an example of a definitely square summable complex sequence? Somebody give me their example. Yeah, so yours is 1, 1/2, 1/3, 1/4. Is that what you said? Okay, and then so that would mean that you're claiming that the sum from 1 to infinity of the magnitude squared of this, that would be 1/n², is not a divergent. It's got to be finite, right? And what do you know about sequences? What kind of series is this? There's a name that you give this kind of series back in calculus. It's not geometric. Geometric series has like, it's something like the sum of a number to the n. So the power is changing, right? First you square it, then you cube it, then you raise it to the 4th. Here it's not the power that's changing. The power is always 2. It's 1/n raised to the 2, but we call that a p series, I think, back in calculus. Is that something you guys at least have back in your memory?
Yes.
There was a theorem that told us which p series converge. They don't all converge. And generally, if you're talking about 1 over a number to a power, as long as that power is anything bigger than 1, if I remember correctly, the p series converges. 1 just barely diverges in a way that we call logarithmically. But if you put a power down in that number in the denominator that's anything bigger than 1, it converges. So this is technically correct. There are lots of other things we could have done. If you like geometric series, we could have done something like this instead. Maybe 1 over the square root of 2, 1 over the square root, let's see, of 4. No. What am I doing here? I want to make 1 plus 1/2 plus 1/4, right? So that seems right. Plus 1/8 when I take the sum of the squares of them, right? 1 over the square root of 8, and so on, right? So I'm taking powers of 2 under the square root there. And then that's going to give me the geometric series when I take the sum from 0 to infinity of the magnitude of Cn squared. That'll give me 1 plus 1/2 plus 1/4 plus 1/8 and so on. And that sums to 2 if you use your geometric series summation formula, I believe. Call geometric series because sometimes you can even think of a geometric argument, right? Here's something of height 1 and width 2. And so here's the first term in the series, the area of this, right? That has area 1 plus 1/2 plus 1/4 plus 1/8. Clearly, it's going to add up to an area of 2. So you can often think of geometric series in terms of geometric diagrams like that. All right, that's a good one. So you could take mine, could take what Jake's was. Let's just stick with this because I've got it up here. Another easy way to make a certainly square summable sequence is to have the tail of the sequence just be all zeros, right? So I might say, 150, 0, 0, 0. You get the idea. Keep those zeros coming on to it. Then for sure it's going to sum to something finite, right? That's, you might say that's cheating, but it's not cheating, right? We're going to find that we use those kinds of things all the time. So the sum of these two sequences would be, I won't even write it down, but the first term would be 2. The second term would be 1 over root 2 plus 50. The third term would be 1 over root 4. The fourth term would be 1 over root 8, and so on. If I scalar multiplied my second sequence, the second example, this should be my second example because that's the one that doesn't have any non-zero things in it. So if I took the scalar 2i and multiplied it by my vector v, that's going to be 2i over root 2, 2i over root 4, and so on. That's just another square summable sequence. How do I know it's square summable? Because the one I could factor that 2i out of the sum, right? And then the sum is perfectly finite. Okay, so that gives examples in 1. Any more questions about 1 or different ways of thinking about it? I'm just giving sequences. A sequence is just, a sequence of numbers separated by commas, and they've got to be square summable. They can't diverge when I add them all up. 2, we're supposed to use capital L2. Somebody give an example of a function in capital L2. Square integrable functions. I might call, again, I could, if I wanted to label them abstractly, usually people don't put equal signs between this and a particular representation because, it's just like saying, if I'm talking about a vector whose components are 3, 1, and 2, if you give the numbers 3, 1, and 2, that's like giving all the components of this vector. People tend to shy away from writing equal signs like that because you don't want to say the vector is the components. That's sort of mixing up two different ways of talking about it. This is the thing we're talking about. And there are lots of different ways to represent it. So a lot of times people will put a colon there and just say, oh, this is the thing we're going to represent in this particular way. I don't have to represent it that way, but it's a definite thing. Okay, what's a square summable, square integrable function? Certainly a Gaussian. That's our number one kind of nice function to write down. There's the simplest Gaussian, if you like. It doesn't have an area 1 under the curve, but it's nice and simple. What's another one? Let's write down a W here. Say that again. E to the what? Sine of x down here. I don't think that's square integrable from minus infinity to infinity. It certainly is from 0 to infinity.
E to the negative x cosine x?
I think that's still going to have problems, right? So what would this function look like? You might don't get overwhelmed by thinking about you realize I have almost no intuition about functions if you haven't thought about these outside the context of calculus. But it can be really fun to just say, what does this function look like if I graphed it? Well, it's sort of like this is the envelope, and this is the function that's wiggling underneath it. Now my envelope looks like this. That's sort of a generic picture of an exponential function. And we've got a sine. It doesn't matter if I have a cosine under it or a sine, right? So this function's going to be behaving nicely over there, but it starts behaving really badly on this side.
True.
And if I take the magnitude squared of it, there's going to be a lot of area under those bumps. It's going to go to infinity.
Wait a minute, I think I have it.
All
E
right.
to the negative absolute value of
That is a good fix, Alvis. That one certainly works because then e to the minus absolute value of x is kind of has this kink in the middle. So it's doing the same thing on both sides. So that would be a good example there. Okay, and we could add them together. You could even draw a graph of the sum, but I don't really want to do it. We could scalar multiply by 2i. Then it would be hard to graph it because it would have complex outputs, but those are the kinds of things we're talking about. Of course, an easy way to make a function square integrable is just to say, well, it's 0 forevermore when x is less than -2 or x is greater than +2. We've done that a lot in my examples that I do just to make your integrals easier. So that's another cheap and dirty way that's sort of like doing this kind of thing, but for a function. 3, give 2 examples in C3. Your second example should be no, I guess I took that out there, but so, you know, these are easy. I just have to give triplets of complex numbers. Hey, real numbers are complex numbers. Here's my second one, 4, 5, 6. The sum is going to be 5, 7, 9. The scalar multiple of the second one by 2i is going to be 8i, 10i, 12i. Just making sure we understand what we're talking about here, right? Don't get lost in the abstraction. We're talking about things you already know how to do. Sometimes coming up with examples can stretch your mind a little bit. All right, 136. Let's see what we have time to do in the last 4 minutes of class. Well, let's just talk about the inner product. The inner product is sort of the highbrow name for the lowbrow name for the same thing as the dot product between 2 vectors. We're going to call it the inner product. That's what mathematicians generally call it. And we're not going to call it the dot product because we're not going to use that dot notation anymore. But a dot product and an inner product kind of mean the same thing. Okay, and there are some axioms that inner products have to satisfy too. And let's look at those. They're equally kind of not too exciting. Inner products, as we noted earlier, there was somewhat of a mystery in the definition of our inner product for functions, and it's related to the first thing there. Oops. Conjugate symmetry. So this is how we're going to denote our inner product, right? So if I have a vector v and w, and I want to take the inner product between them, there are actually 2 ways I could do it. One of them is denoted like this, and the other one is denoted like this. And they're not the same in general, although they can be the same as long as your vectors are real vectors, if it's a vector space over real numbers. But in general, they're related by a complex conjugation. So if you take the inner product one way, take the inner product the other way, those 2 numbers are complex conjugates of each other. But if it's a real vector space, that means it's a vector space with real coefficients out in front, then this will be symmetric. And the other things, well, linearity isn't too exciting. That's just sort of distributing over things in the inner product, right? If I take v times 2w, v dotted into 2w, that's the same thing as 2 times v dotted into w. Same things you would have already assumed there, right? And finally, this is an important one. Every inner product has to be positive definite. That means if you take an inner product of a vector with itself, it has to be greater than or equal to 0. That means it's a real number and a non-negative real number. And the only case where the inner product of a vector with itself is 0 is when the vector itself is the 0 vector. Okay, those are all things that are trivially satisfied for our usual dot product. So, for example, if we take these 2 elements of C3, and so suppose I call this my V here, and this my W. Well, actually, I think I have a voting question here. Let's just end with that voting question. because this is about complex vector space. This is about a vector in what I would have called C2, a two-dimensional complex vector space. Those V1 and V2 in the doublet or the two tuple there are complex numbers. So they're what we would normally call the components of the vector. If we want the inner product of a vector with itself to be positive for non-zero V and 0 only for the 0 vector, what is a formula that's going to work for the inner product between the component, between a vector that has components A1 and A2 and a vector that has components B1 and B2? We're out of time, so just show me a vote if you've got one.